Alright, welcome to what may quite possibly be the last video of Chapter 3. We're going to talk about normalization of a vector. Sometimes it will be useful to change the unit of scale of a vector, while of course preserving the proportional relationships of its elements, which is what makes it an eigenvector. This change in scale is referred to as normalizing the vector. One example of where this is useful is in the process of extracting the eigenvectors of a matrix. Eigenvectors are defined only up to an arbitrary multiplier. For example, if the first eigenvector of, let's say, a matrix S were to come out to be x equals, we have the values 1, 4, 3, 2. Sorry, that's a funny looking eigenvector. Then this eigenvector could also be expressed as y equals 2, 8, 6, 4, which is, if you notice, is 2 times x. The proportionality among the elements is preserved in this transformation of x into y by just, for example, doubling each element. If x is an eigenvector of matrix S, then y is also an eigenvector of matrix S. That's important to know, as any other vector created by multiplying the elements of x by some constant. So if you multiplied x by 3, and you had 3, 12, 9, and 6, and we called that z, which I'll just write over here, 3, 12, 9, and 6, which is just x times 3. That z can also be considered an eigenvector of matrix S, or whatever matrix this is of. The way we specify which version of the eigenvector is wanted is by specifying what it is normalized to. By definition, its sum of squares is what it is normalized to. So let's take the sum of squares of x. And that will equal 1 squared plus 4 squared plus 3 squared plus 2 squared. So we're just squaring each element and adding them together, which gives us 1 plus 16 plus 9 plus 4. You add those up, and it's 20, you get 30. So vector x is thus normalized to 30, while the vector y, we can see what that is normalized to. 2 squared plus 8 squared plus 6 squared plus 4 squared. That's 4 plus 64 plus 36 plus 16, which will give us 120. So x is normalized to 30, and y is normalized to 120. Often we wish to normalize a vector to 1. This is done by dividing each element of the vector by the magnitude of that vector. That is, the magnitude is the square root of the value to which it's currently normalized. For example, if we wish to convert vector x here, which is currently normalized to 30, that we just found, if we want to convert vector x to be normalized to 1, the number 1, we would divide each element of the vector by the magnitude of that vector, which is the square root of 30. So we've got magnitude is the square root of the value to which it is currently normalized. That's important to know. So we can have, let's say, vector x normalized, and that's going to be, we're going to take this first value, 1, and divide by the square root of 30. So divide by the magnitude, the square root of the value to which it's currently normalized. Then we're going to take 4 and divide it by a square root of 30. The next element is 3, and then 2. So let's take the sums of squares of this one. So the sums of squares of x norm is going to be 1 over square root of 30 squared plus 4 over square root of 30 squared, 3 over square root of 30, that's squared, and the last element squared. Which gives us 1 over 30 plus 16 over 30 plus 9 over 30. Obviously these are all going to be over 30, plus 4 over 30, which is equal to 1. So the sum of squares of this normalized vector x is 1. So that's how you successfully normalize that. So unless we otherwise specify it, when we say normalized, we mean normalized to the number 1. Otherwise, we would specify it. For example, we can say normalize the vector to 5 or something like that. Now, I just wanted to mention before we finish here that in a previous video on spectral decomposition, that was video 3.38, we did mention, I briefly mentioned, that we had a matrix C, and matrix C is the matrix of normalized eigenvectors. And I did mention that they're normalized to 1. So in fact, we actually have used normalization of vectors. We just didn't describe how to get it. But now you know. So there you go. I hope you had fun studying Chapter 3, Fundamentals of Matrix Algebra. It's really fun to do. And you'll see later on even more application of the principles that we talked about. Hope you have a wonderful day.